Welcome! In this session, we'll dive into problem number 934, shortest bridge, a fascinating challenge that combines grid traversal and algorithmic optimization. Get ready to explore some intriguing strategies to solve this problem efficiently. In this problem, you are given an nxn binary matrix called grid, where each cell can either be a 0, representing water, or a 1, representing land. Within this grid, there are exactly two islands, and each island is made up of a group of ones that are connected either horizontally or vertically. These islands are completely surrounded by water, meaning they are disconnected from each other. The task is to determine the smallest number of water cells, those with a value of 0, that need to be flipped into land cells, or 1s, in order to create a bridge that connects the two islands. Since the problem guarantees that there are always exactly two islands, you can assume that it is always possible to find a solution. The input for this problem is the grid itself, which is a 2D list of integers, and the size of the grid can range from 1 to 100. The output is a single integer, which represents the minimum number of zeros that must be flipped to connect the two islands. To better understand the problem, let's look at the first example. Here, the input grid is a 2 by 2 matrix, where the top right cell and the bottom left cell are land, represented by 1s. These two ones form two separate islands. The first island is made up of the single cell located at coordinates 0, 1, and the second island consists of the single cell at coordinates 1, 0. To connect these two islands, you can flip the water cell at 0, 0 into land. By doing this, a bridge of length 1 is formed, connecting the two islands. The output in this case is 1, as only one water cell needed to be flipped. Now let's examine the second example. Here, the grid is a 3 by 3 matrix, and it contains two islands, one at the top center cell, 0, 1, and the other at the bottom right cell, 2, 2. To connect these islands, you need to flip two water cells. Specifically, you can flip the cell at 1, 1, which lies between the two islands, and then flip either the cell at 0, 2, or the cell at 2, 1. By flipping these two cells, you create a bridge of length 2, which is the shortest possible connection between the two islands. So the output for this example is 2. In the third example, the grid is a 5 by 5 matrix. Here, the first island forms a square that surrounds the perimeter of the grid, while the second island is the single cell located at the center of the grid, at 2, 2. To connect these two islands, you can flip any one of the water cells that are directly adjacent to the center cell. For instance, flipping the cell at 2, 3, or 3, 2, would create a bridge of length 1, which is the shortest possible connection. The output for this example is therefore 1, as only one water cell needs to be flipped. To summarize, the problem comes with a set of constraints that you need to keep in mind while designing your solution. First, the grid is always square, meaning the number of rows equals the number of columns, and the size of the grid ranges from 1 to 100. Second, each cell in the grid can only be 0 or 1, and there are always exactly two islands. Finally, there are a few edge cases to consider. For instance, if the grid size is 1, the problem does not apply because it's not possible to have two islands. Additionally, islands can be located at the edges or corners of the grid, and they may have irregular shapes, which means they're not always square or rectangular. Lastly, for larger grids with up to 10,000 cells, your solution must be efficient enough to handle these inputs within a reasonable time frame. There are a few more scenarios to account for. The two islands can take on non-uniform, irregular shapes, meaning that their boundaries might be jagged or uneven. This adds complexity to the problem since you'll need to carefully identify and differentiate the two islands. Additionally, when dealing with the largest possible grid size of 100 by 100, your algorithm must be optimized for performance to handle up to 10,000 cells efficiently. This means you'll need to implement a solution that not only finds the shortest bridge but does so without excessive computational overhead, ensuring that it works well for both small and large grids. To tackle the shortest bridge problem, we first consider the brute force approach. This method is intuitive but inefficient. The idea is to identify both islands on the grid and calculate the Manhattan distance between all pairs of points, one from each island. For every cell with a value of 1 in the first island, we compute the distance to every cell with a value of 1 in the second island. The shortest bridge is determined by finding the minimum distance among all pairs and subtracting 1 to exclude overlapping cells. While this approach directly aligns with the problem definition, it has significant drawbacks. Specifically, its time complexity is O(n to the power of 4, which stems from the O(n squared) cost of identifying the islands and the nested loops required for pairwise distance calculations. This makes it impractical for larger grids due to the exponential growth in computation time. As a result, we need a more efficient solution to handle this problem effectively. Now, we turn to a more optimized method that uses BFS or DFS for island identification and multisource BFS for the shortest bridge calculation. The first step is to identify all the cells belonging to one island. This can be done using either DFS or BFS to traverse the grid and mark the cells of the first island, for instance, by changing their value from 1 to 2. Once the first island is marked, we proceed to the second step, expanding outward from the boundary of the first island using a multisource BFS. This means we treat all the boundary cells of the marked island as the starting points and explore layer by layer. As the BFS progresses, we count the number of layers until we encounter the second island. This approach ensures that we find the shortest path because BFS inherently explores all possible paths in increasing order of length. The time complexity of this method is O(n squared, as each cell in the grid is processed at most once, and the space complexity is also O(n squared, due to the queue and visited structures used in the BFS algorithm. This makes it significantly more efficient than the brute force method. The strategy we chose for solving this problem is the optimized approach that combines BFS or DFS for island identification with multisource BFS for finding the shortest bridge. This method stands out because it reduces the time complexity from O(n to the power of 4 in the brute force approach to O(n squared, making it far more efficient. It also aligns perfectly with the problem's requirements, ensuring that the shortest bridge is calculated in an optimal manner. The use of BFS guarantees that the shortest path is found, while marking one island simplifies the process by preventing any ambiguity during traversal. However, there are some trade-offs to consider. While the brute force method is conceptually simpler, its computational cost makes it unsuitable for larger grids. On the other hand, the optimized approach requires additional logic for marking islands and managing the BFS queue, but these complexities are justified by the substantial performance gains. Between DFS and BFS for island identification, BFS is generally preferred because it avoids potential stack overflow issues in large grids, which can occur with the recursive nature of DFS. The key insight that simplifies this problem is recognizing that it can be divided into two distinct phases: first, identifying the islands, and second, calculating the shortest path between them. The aha moment lies in realizing that a multisource BFS eliminates the need for exhaustive pairwise distance calculations, which makes the solution both efficient and optimal. By marking one island and expanding outward layer by layer, we can ensure that the shortest bridge is found without redundant computations. In summary, the optimized BFS-based strategy is ideal for this problem due to its efficiency, scalability, and alignment with the problem requirements. While alternative methods like brute force or DFS-only solutions exist, they fall short in terms of performance or robustness when applied to larger grids. The BFS-based approach strikes the right balance, making it the most suitable choice for solving the shortest bridge problem effectively. The problem challenges us to connect two islands in a binary matrix by flipping the minimum number of water cells into land cells, effectively creating the shortest bridge between the two islands. Here, land is represented by 1, and water is represented by 0. To solve this, we'll use a combination of depth-first search, or DFS, and breadth-first search, or BFS. In the first step, we identify and label the two islands. Using DFS, we traverse through the matrix, starting with the first land cell we encounter. We mark all the connected cells of this first island with a new label, such as 2, to differentiate it from the second island. During this traversal, we also gather all the water cells immediately surrounding the first island. These boundary cells will form the starting points for the BFS, which will help us calculate the shortest path to the second island. Once we've identified the two islands and collected the boundary cells of the first island, we proceed with the BFS step. The BFS algorithm expands outward from these boundary cells, level by level. For each cell in the queue, we explore its neighboring cells in all 4 directions: up, down, left, and right. If we encounter a cell belonging to the second island, which means its value is 1, we know we've found the shortest bridge. The BFS level at this point gives us the minimum number of water cells that had to be flipped. If a neighbor is instead a water cell, we mark it as visited, add it to the queue, and continue expanding. This process ensures that we explore all cells at the current distance before moving to the next, guaranteeing that the path we find is indeed the shortest. The search terminates as soon as we reach the second island, providing an efficient solution. To implement this algorithm effectively, we rely on a few key data structures. First, the input matrix itself is used to store the grid, and it is modified in place to mark visited cells. Second, a queue is used during the BFS step to manage the boundary cells and their expansions. Instead of maintaining a separate visited array, we mark visited water cells directly in the matrix. The algorithm involves two main operations, the DFS traversal to mark the first island, and the BFS traversal to find the shortest bridge. Both operations have a time complexity of O and *m, where n and m are the dimensions of the matrix. This is because each cell is visited at most twice, once during DFS and once during BFS. The space complexity is also O and *m in the worst case, due to the queue used in BFS, but this is optimized by only starting the BFS from the boundary cells. The algorithm also handles edge cases, such as when the islands are directly adjacent, requiring no bridge, or when they are separated by a large body of water. Let's walk through an example to understand the process better. Consider the given matrix. The first step is to use DFS to identify and mark the first island. By starting from the first land cell, we label all connected land cells of the first island as 2. The updated matrix shows the first island marked, and the boundary cells identified for BFS are at positions 0, 1, and 1, 1. Next, we initiate the BFS to find the shortest bridge. In the first level of BFS, the boundary cells expand outward, and their neighboring water cells are added to the queue. The updated matrix shows the progression, with the cells closest to the first island being marked as part of the BFS traversal. At this point, the BFS encounters a cell belonging to the second island, indicating that the shortest bridge has been found. The BFS level at this stage is 1, meaning the bridge length is 1. This is the minimum number of water cells that need to be flipped to connect the two islands. The final answer for this example is a bridge length of 1, demonstrating the efficiency of the algorithm in finding the shortest path. To solve the shortest bridge problem, we first need to identify the two islands in the grid. We'll begin by determining the dimensions of the grid, its rows and columns. To locate the first island, we use a depth-first search, or DFS, which explores all connected land cells. The DFS function marks each visited cell as -1 to indicate that it belongs to the first island. This marking ensures we don't revisit these cells later. The function also recursively explores all 4 possible directions up, down, left, and right from the current cell. By doing this, we effectively isolate the first island and prepare it for the next step, which is the breadth-first search, or BFS. The BFS function is used to find the shortest path from the first island to the second. We start by adding all the cells marked as -1 from the first island into the BFS queue. Each entry in the queue contains the cell's coordinates and its current distance from the first island. As we process the queue, we check all neighboring cells. If we encounter a cell with a value of 1, it means we've reached the second island, and the current distance is returned as the result. If the neighboring cell is water, represented by 0, we mark it as visited by changing its value to -1 and add it to the queue with an increment distance. Finally, we combine this BFS with the earlier DFS by first locating the first island in the grid, marking it, and then running the BFS to find the shortest bridge. The result of the BFS is the minimum number of steps required to connect the two islands. Here we begin our Java implementation of the shortest bridge problem. First, we import the required utilities and define our solution class. The main method shortestBridge takes a 2D grid as input, representing the binary grid of islands. We start by determining the number of rows and columns in the grid. Then, we use a nested loop to locate the first island. Once we find the first cell of the island, we use a depth-first search, or DFS, to traverse and mark all the cells of this island with a value of -1. This marking helps us distinguish the first island during the subsequent breadth-first search, or BFS. To ensure we stop as soon as we've processed the first island, we use a found flag to exit the loop early. Finally, the BFS method is called to calculate the shortest path to the second island. Let's see how the DFS method is implemented next. The DFS method is a recursive function that helps us traverse the first island. It takes the grid, the current cell coordinates, x, y, and the grid dimensions as inputs. The first check ensures we are within bounds and that the current cell is part of the first island, i.e., its value is 1. If these conditions are not met, the recursion terminates for that path. Once we confirm the cell is valid, we mark it as part of the first island by setting its value to -1. Then, we define the 4 possible directions up, down, left, and right and recursively call DFS for each neighboring cell. This ensures that all connected cells of the first island are visited and marked properly. After marking the first island, we move to the BFS method, which is responsible for finding the shortest bridge. The BFS method uses a queue to perform a breadth-first search. First, we initialize the queue by adding all cells that belong to the first island, which are marked with -1. Each cell in the queue is represented as an array containing its coordinates and the distance traveled so far. From there, we define the same 4 possible directions for movement up, down, left, and right and start processing the queue. For each cell, we calculate the coordinates of its neighbors and check if they are within the grid bounds. If we encounter a cell from the second island, indicated by a value of 1, we immediately return the current distance as the shortest bridge. If the neighbor is water, represented by 0, we mark it as visited by setting its value to -1 and add it to the queue with an increment distance. This process continues until the second island is found. If, for some reason, the loop exits without finding the second island, we return -1, although this case should never occur in a valid input. In this example, we are working with a small 2x2 grid that contains 2 islands separated by a single water cell. First, we initialize the basic variables, rows and calls are both set to 2. The grid structure makes it clear that we have 2 distinct islands. Our goal is to connect these 2 islands by flipping the minimum number of water cells. To achieve this, we start by identifying one of the islands using depth-first search, or DFS. Beginning at grid 0, 1, which is part of the first island, we mark this cell as -1 to indicate it has been visited. From there, we recursively explore its neighbors. For example, we move to grid 1, 1, marking it as -1 as well. Once the DFS completes, the grid is updated to reflect the first island is visited, with the new state being 0, -1, -1, 0. This prepares us for the next step, where we'll focus on finding the shortest path to the second island. The next phase involves using breadth-first search, or BFS, to determine the shortest path from the first island to the second. We start by initializing the BFS queue with all cells that are part of the first island, which in this case are 0, 1, 0, and 1, 0, 0. These tuples represent the row, column, and the initial distance of 0. We then begin processing the queue. First, we dequeue 0, 1, 0, and examine its neighbors. One of its neighbors, grid 1, 1, has already been visited, so we skip it. Another neighbor, grid 0, 0, is a water cell, so we expand to this cell, marking it as -1 and adding it to the queue. Next, we dequeue 1, 0, 0, and examine its neighbors. Here, we find that one of its neighbors, grid 1, 1, belongs to the second island. This means we've successfully found a path, and the shortest distance is 1. The final output for this example is therefore 1. Now, we move to a larger grid example, where the dimensions are 4 by 4. This grid contains 2 islands that are farther apart. As before, we start by initializing the variables rows and calls, both set to 4. Using DFS, we identify the first island, beginning at grid 0, 0. All connected cells that belong to the first island are marked as -1. This includes grid 0, 1, and grid 1, 0, which are connected directly to grid 0, 0. After completing the DFS, the grid is updated to reflect the visited cells of the first island, with the new state being -1, -1, 0, 0, -1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1. Next, we initialize the BFS queue with all the cells belonging to the first island, 0, 0, 0, 0, 1, 0, and 1, 0, 0. These cells will serve as the starting points for expanding toward the second island. We now process the BFS queue to find the shortest path to the second island. First, we dequeue 0, 0, 0 and expand to its neighbor grid 1, 1, which is a water cell. This cell is marked as -1 and added to the queue. Next, we dequeue 0, 1, 0 and expand to grid 1, 2, another water cell, which is also marked as -1 and added to the queue. Then, we dequeue 1, 0, 0 and expand to grid 2, 2, continuing the process. Finally, as we expand further, we reach grid 2, 3, which belongs to the second island. This indicates that the shortest path has been found, and the total distance is 3. The final output for this example is therefore 3. In this problem, the solution revolves around two main steps. First, using depth-first search, or DFS, to identify and mark the first island, and second, using breadth-first search, or BFS, to determine the shortest bridge to the second island. Let's start with the DFS step. Here, the algorithm explores all the cells that belong to the first island, visiting each cell exactly once. If we consider the grid size to have dimensions rows and cols, the total number of cells in the grid is n equals rows * cols. Now, let's assume the first island occupies k cells. The DFS traversal is limited to these k cells, meaning it operates in O(k) time. In the worst-case scenario, where the first island spans the entire grid, k equals n, so the time complexity for this step is O(n). Next, we move to the BFS step. Starting from the k cells of the first island that were marked, BFS explores the neighboring cells level by level in all four directions. Each cell is processed once, and if it's already visited, it's skipped. In the worst case, BFS might examine all n cells of the grid before locating the second island, leading to an O(n) time complexity for this step as well. Adding the time complexities of the DFS and BFS steps, we get O(n) plus O(n), which simplifies to O(n). Now, let's consider space complexity. For the DFS step, the algorithm relies on a recursive call stack. In the worst case, the recursion depth matches the size of the first island, which is k. Since k is at most n, the DFS stack requires OK, or O(n) space. For BFS, the algorithm uses a queue to manage the cells being processed. Initially, this queue holds the k cells of the first island, but as the BFS progresses, it may expand to include up to all n cells of the grid. Therefore, the BFS queue also requires O(n) space in the worst case. Additionally, the algorithm modifies the grid in place to mark visited cells, so no extra memory is used for this purpose. Putting it together, the total space complexity is dictated by the larger of the DFS stack and the BFS queue, both of which are O(n). When we consider the overall space complexity, it is clear that the DFS stack and BFS queue dominate, each contributing O(n). Thus, the total space complexity remains O(n). Now let's compare this optimized approach to a brute force method. A naive solution would involve calculating the shortest distance between every pair of cells belonging to the two islands. This results in a time complexity of O(n², as it involves checking all possible pairs of cells. However, this brute force approach has a very low space complexity of O(1), since no additional data structures are used. In contrast, our optimized approach achieves a significant improvement in time complexity, reducing it to O(n), while the space complexity increases slightly to O(n), due to the use of the DFS stack and BFS queue. This trade-off is worthwhile for the substantial gains in efficiency. Now let's analyze the algorithm across different scenarios. In the best case, the two islands are adjacent, and BFS connects them immediately. However, the DFS step and BFS initialization still require O(n) time overall. In the average case, the islands are separated by a moderate distance, requiring BFS to traverse some water cells. Even here, the time complexity remains O(n). In the worst case, the islands are located on opposite ends of the grid, forcing BFS to explore nearly all n cells before finding the second island. Despite this, the time complexity is still O(n), and the space complexity remains O(n). Finally, let's validate the big O analysis mathematically. Both DFS and BFS process each cell at most once, making the total operations proportional to n. The space usage is similarly bounded by the grid size and the auxiliary structures like the stack and queue, both capped at O(n). This confirms that the time complexity is O, n, and the space complexity is also O, n. When working on the shortest bridge problem, there are a few common mistakes that can trip you up. First, you need to ensure that the two islands are identified correctly. Many solutions fail to distinguish between the two islands, which leads to incorrect bridge calculations. A reliable method like DFS or BFS is crucial to properly mark and separate the cells of each island. Next, it's important to be mindful of edge cases. For example, in very small grids, such as 2x2, the islands might already be adjacent. You should also handle scenarios where there's only one island or no islands at all. Additionally, don't overlook cases where the islands are already connected, as these can subtly break your solution. Another common pitfall is using inefficient brute force methods to calculate the shortest bridge. Comparing all pairs of points between the two islands results in O, n to the power of 4, complexity, which is impractical for larger grids. Instead, optimize your approach with techniques like BFS, which focuses the search on the island boundaries. Finally, incorrect distance calculations can lead to errors. Always use the Manhattan distance formula, which is the absolute difference in x coordinates plus the absolute difference in y coordinates, to ensure accuracy. Another point to keep in mind is properly terminating your BFS search. If you fail to stop the BFS as soon as the shortest bridge is found, you'll end up performing unnecessary computations, which can significantly increase the runtime. Using a queue and stopping the search as soon as you reach the nearest point of the other island is key. Now, let's consider the bigger picture. This problem combines two essential patterns: identifying connected components, which is done during island identification, and performing a shortest path search, which is used for bridge calculation. Proficiency with DFS and BFS is critical for solving this problem efficiently. The two-phase approach is particularly effective here. First, use BFS or DFS to identify the islands. Then, expand outward from one island using BFS to determine the shortest bridge. To optimize the BFS, ensure you mark nodes as visited and manage the queue carefully to avoid redundant checks. It's also helpful to understand the trade-offs between different approaches. While brute force is easier to implement, it's highly inefficient. BFS, on the other hand, strikes the right balance between performance and complexity, but it does require careful queue management. To deepen your understanding of this problem, you can explore related problems on LeetCode. For example, Problem 200, Number of Islands, focuses on connected components, while Problem 695, Max Area of Island, is another variation that emphasizes island traversal. Problem 1034, Coloring a Border, and Problem 286, Walls and Gates, also involve grid-based searches with BFS and DFS, making them excellent practice. Now, let's briefly discuss alternative approaches and their trade-offs. The brute force method, which checks all pairs of points between the two islands, is conceptually simple but has a staggering O, n to the power of 4, complexity, making it unsuitable for larger grids. A more effective approach is optimized BFS, which reduces the complexity to O, n squared, by expanding from the boundary of one island. This method is faster and more efficient, but it requires additional bookkeeping to manage the queue and track visited nodes. Lastly, while union find, or disjoint set union, can theoretically be adapted for this problem to merge islands, it's rarely used in practice and often introduces unnecessary complexity. Overall, BFS is the go-to solution due to its balance of simplicity and efficiency for grid-based shortest path problems. Great job! To recap, we discussed solving the shortest bridge problem using BFS and DFS, analyzed its complexities, and highlighted when these techniques are applicable. Thank you for joining, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!